Welcome back to Tech Talk Today, where we dive into the captivating world of technology and data management. I'm your host, Your Name, and today we're going to unpack some essential concepts surrounding data reliability and transactions. We'll explore why writing data to disk remains crucial, the significance of transactions in databases, and how we can ensure data integrity in our increasingly complex digital landscape. So grab your headphones and let's jump right in. Let's start with data storage. Picture this. You've just saved your work to disk, and then, out of nowhere, your machine crashes. While the data is technically safe on that disk, it's completely inaccessible until you either fix the machine or transfer the disk to another one. This scenario illustrates a major challenge in data management, ensuring availability even when failures occur. This is where replicated systems come into play. Replication helps us maintain data availability even if one part of our system fails. However, there's a catch. If a correlated fault happens, like a power outage or a bug that crashes every node under specific conditions, all replicas could go down at once. This means that any data stored only in memory could be lost. So while writing to disk is essential, especially for in-memory databases, it's not a foolproof solution. Now, let's delve a bit deeper into the technical aspects. In an asynchronously replicated system, there's a risk of losing recent writes if the leader node becomes unavailable. This is a critical consideration, as it can lead to data inconsistency and loss. Speaking of data loss, let's talk about solid-state drives, or SSDs. Research has shown that when power is suddenly cut, SSDs can sometimes fail to deliver the guarantees they're supposed to provide. Even the fsync command, designed to ensure data is written to disk, can falter under such conditions. Moreover, subtle interactions between the storage engine and the file system can lead to bugs that are tough to track down. These bugs can result in corrupted files after a crash, which is a nightmare for any data manager. And here's something to keep in mind. Data on disk can gradually become corrupted without anyone noticing. If you're not vigilant, you could end up with corrupted replicas and backups, making recovery a daunting task. In those situations, you might need to restore data from historical backups, which can be time-consuming and complex. Now let's talk numbers. Research indicates that between 30% and 80% of SSDs develop at least one bad block within the first 4 years of operation. While magnetic hard drives have a lower rate of bad sectors, they tend to fail more often overall. And if an SSD loses power, it can start losing data within weeks, especially in warmer temperatures. So what's the takeaway here? In practice, there's no single technique that guarantees absolute data safety. Instead, we need to rely on a combination of strategies: writing to disk, replicating data to remote machines, and maintaining backups. It's essential to use these techniques together to effectively mitigate risks. Always keep in mind that theoretical guarantees should be taken with a grain of salt. Now let's shift gears and discuss transactions. You might be wondering, what's the big deal about transactions? Well, consider this. If you're using an email application and your unread message counter is incorrect, it may not seem like a huge issue. But when it comes to financial transactions, like a customer's account balance, accuracy becomes absolutely critical. When a client makes several writes within a single transaction, the database ensures that if something goes wrong, all those writes can be rolled back. This all-or-nothing guarantee is vital for maintaining data integrity. We want to ensure that concurrent transactions don't interfere with each other. For instance, if one transaction is updating a counter while another is reading from it, we want to make sure that the reader sees either all of the updates or none at all, never a partial state. This is especially important with multi-object transactions. In many applications, several pieces of data need to be kept in sync. For example, if an email application tracks the number of unread messages in a separate field, both the message and the counter need to be updated together. If the counter increments but the message isn't inserted correctly, users might see an inaccurate count of unread messages. Now, consider what happens if a network connection drops during a transaction. If the transaction is aborted midway, the client might not know whether it was committed or not. This is where a transaction manager comes into play, grouping operations by a unique transaction identifier independent of the connection. Let's discuss atomicity and isolation. Atomicity ensures that if an error occurs during a transaction, any prior writes are undone to prevent an inconsistent state. Isolation, on the other hand, prevents transactions from interfering with each other, which is crucial for maintaining data integrity. However, not all databases implement these concepts uniformly. While relational databases typically use a client's TCP connection to determine transaction boundaries, many non-relational databases lack this feature. Even if they offer multi-object operations, they may not guarantee transaction semantics, leaving the database in a partially updated state. Atomicity and isolation also apply to single object changes. For instance, if you're writing a large JSON document and the network connection drops halfway, what happens to that data? Does the database store an incomplete document? These scenarios highlight the importance of having robust transaction management in place. So, do we really need multi-object transactions? While some applications can operate with single-object transactions, many require coordination across multiple objects. In relational databases, foreign key references must remain valid, and in document databases, denormalized data often needs to be updated together. Transactions help keep this data synchronized and prevent inconsistencies. That said, implementing transactions can be challenging, especially in distributed databases. While it's possible, it often comes with trade-offs in terms of availability and performance. In conclusion, while we can't guarantee absolute data safety, we can employ a range of risk reduction techniques. Writing to disk, replicating data, and maintaining backups are all essential strategies in our toolkit. And when it comes to transactions, understanding their role in maintaining data integrity is crucial for any application, especially those dealing with critical data. Thanks for tuning in to today's episode of Tech Talk Today. I hope you found this discussion insightful. Don't forget to subscribe and share this podcast with your fellow tech enthusiasts. Until next time, keep exploring the fascinating world of technology.